Okay, so you should get intuitive sense for another property of complexity called emergence. I used the term emergent solutions already, so let's read a bit about emergence here. The different levels of complexity we observe in the hierarchical aggregation of interacting elements are not arbitrary but guided by the emergence of observable properties that cannot be reduced to the constituent elements and interactions on the level below. So every element has certain range of, let's say, observable properties and behaviors, but when you combine the elements into a system, the complexity can produce something that is not expected from just each element. So that's something, it's called emergent. In other words, it's not a coincidence that we identify the ant colony as a level of complexity above the myriad of interacting ants, or the brain as about 86 billion interacting neurons. So we said how brain has all these parts: the neocortex, the amygdala, the limbic part, the left brain, light brain, with 86 billion neurons. But then the brain is making me do all these things, say all these things, communicate with you this way, read the material, and so on. We recognize the ant colony because it exhibits remarkable ingenuity in solving the problems it encounters, as we'll see in a minute. At the same time, as each ant has minimal behavioral portfolio with significant randomness in terms of activities. So if we just look at one ant wandering around looking for food or whatever, you don't get a sense of what the colony can do when it gets together in such large numbers. We recognize the ant colony, okay, because of that remarkable ingenuity. The resilience of the ant colony is, in other words, an emergent property allowing the ant colony to survive over long periods and regular exposure to various hazards, even when each ant almost always dies when circumstances do not fit its behavior. So there's a lot written about these eusocial insects like bees, ants, and so on by Edward O. Wilson, who died a few years ago. He spent his whole life studying these eusocial animals which live together and breed kind of in a way where each ant is not fighting for its own production or its own propagation of genes, but the queen ant, queen bee, and so on are being served by certain procreators, and there are a lot of worker ants that are just serving the purpose of the colony. So it's a very incredibly complex structure that's organized to accomplish so much. So that's the resilience. That said, there may be other levels of complexity that could be interesting for other purposes, regardless of which the complex behavior of the whole regardless of which the complex behavior of the whole emerges in the simple actions and interactions of the parts. Similarly, we identify the brain because human consciousness emerges in the electric impulses between all those neurons, and the rock concert stampede because the dangerous and uncontrollable crowd movements emerge in the benign dancing of the thousands of individuals. There are other ideas about how we have a collective brain, so we can invent things together, and it's a non-zero sum game. So I have mentioned this before, where somebody invents something, they sell it to you, they make money, you buy it because you can use it to make money. So it's not a zero-sum game in that sense. So the collective brain can work together for good and for bad. So collective brain is functioning when you're all dancing together and having fun, and then something happens and then stampede can happen, people can die. This emergence of properties of the whole that cannot be reduced to its parts is perhaps the paramount manifestation of complexity. So I hope you get some sense from those examples. Here is a nest of ants hanging in a tree in Kranzkloof Nature Reserve of South Africa. There are ants, termites for example, build colonies underground, and there are nice YouTube videos that show how they could pour literally some 3 trucks of cement to fill the ant colony. That's how complicated the structure was. It's actually an underground city of complex network of chambers and pathways and so on, and ants protected from outside attack from water. They have suicidal behavior where they can go and kill themselves to attack the enemy. If they get sick, they go away and die somewhere else. They can produce chemical weapons, and they can do agriculture by collecting water and harvesting mushrooms of some kind, and so on and so forth. Okay, so the remaining issue regarding the emergent properties of complex systems concerns the circumstances of direct causal links between them. It is perhaps obvious that one emergent property can influence another directly if the two are emergent properties of two different systems. They are then simply properties of two interacting elements on a higher level of complexity. It is less straightforward when the two emergent properties emerge in the same complex system or in the interaction of the same two elements. Under such circumstances, the possibility of a direct causal link depends on whether the emergent property itself can be considered endowed with the causal powers or not. Sounds kind of convoluted, but without examples that gets a bit too wordy. It's not easy to imagine relevant emergent properties with their own causal powers in the complex systems of primary interests in this book. Still, there are arguments both for and against regarding the brain. Without their own causal powers, any observed association between emergent properties of the same complex system must be indirect and explained with reference to its interacting elements. You can read these papers for understanding what is meant. Coleman's now classic example of Weber's suggested causal link between Protestant religious doctrine and the capitalist economy is an informative illustration of this. Whilst an association between these two elements, capitalism and Protestantism, these two emergent properties can be observed in the 19th century societies in Europe. So we can look at link 1 in figure 9.7 in a minute, explaining that it requires us to understand how the Protestant doctrine influenced individual values. So link 2 is talking about the downward causation here, and how these values influence the myriad economic activities of Protestant individuals, which is shown in link 3, and how the capitalist economy emerged in the interactions between these economic activities. So link 4 is the emergence here. So we'll see that in the next page. Even if all three steps are equally important for explaining the observed association, the last step, or the emergence, has been the most challenging. Emergence may not be only paramount manifestation of complexity, but also the most demanding for us to grasp. So here is an example of an observed association between two emergent properties explained as a chain of causal links across levels of complexity. So you have emergent property up here. So start with Protestant religious doctrine, which has a putative connection with capitalist economy, but it is coming through individual values with interacting elements, or individual Protestants are interacting with each other and also with non-Protestants, and that leads to economic activities, and then that has led to presumably capitalist economy. So that this link is convoluted, but is an emergent property here of the Protestant religious doctrine. There are other implications made about how Hinduism doesn't have a central authority and is a religion in the cloud, because there is no central authority, so it behaves very differently compared to something like a Protestant religion with its doctrines and authorities and so on and so forth. So path dependence as such is closely related to the idea of a lock-in effect, in which the path dependence results in such a strong anchor point that it is onerous to move forward. So it's hard to go forward without understanding this lock-in effect. There are numerous examples of such lock-in effects, out of which the prevailing dominance of the QWERTY keyboard, regardless of superior alternatives, is the archetypical example. So people keep coming up with different shapes and different arrangements of keyboards, but the QWERTY keyboard has remained robust since 1878 or even before that. So the QWERTY typewriter key layout from 1878 has remained essentially the same even now in the 21st century, even though this is now used on iPhones, on smartwatches, on computers, on everything you can think of, and yet it hasn't changed in its archetypical original invention. There are of course many other lock-in effects that are of more direct relevance to the context of this book. For instance, IPCC presents lock-in effects of fossil fuel related infrastructure as critical for long-term mitigation strategies. It highlights how inappropriate responses to climate change lock in high levels of vulnerability and risk. So the inappropriate responses to climate change tend to lock in the high levels of vulnerability and risk. Lock-in effects are identified in continuing production of chemicals despite strong imperatives for reduction. You can think of plastic, which is a miracle material, polluting everything, and the microplastics, nanoplastics are even in our bloodstream and so on, but we still don't stop producing them and using them. And this is essential to anticipate and avoid when adopting infrastructure systems, and yet we are locked into those. In short, it's not enough to just state that history matters. We need to consider how it matters and how we are often locked into it despite its well-known negative impacts on our very being. Okay, so we'll come back and look at how complexity also gives us self-organization. This comes up a lot in climate patterns and so on, and can be used for making predictions. For example, if you want to think about monsoon predictions, and if the monsoon system has self-organizing patterns, then there are statistical ways in which you can extract those patterns and use them to make predictions at various time scales. So despite a complex system being so unpredictable, you can have self-organizing patterns that can be used for predictions. So we'll come back and discuss that. Okay, see you in the next